If you study in dual award science or combined science with Edexcel, you're in luck, because I'm going to go through the entire chemistry paper 1 with you, and what I suggest you do is for each question, pause the video, have a go at the question either in your head or write it down on a piece of paper, and then replay the video and see how you got on. So let's get started. So we're going to look at the 2024 Chemistry Paper 1. Although it says Paper 2 on the front, it's just the way Edexcel number them. This is what we traditionally think of as Paper 1 content. Question 1. Barium hydroxide reacts with dilute hydrochloric acid to form barium chloride solution and water. Complete the balanced equation for the reaction by adding a number in front of HCl. So that is reminding you that when we're balancing equations, we can't start messing about with these small numbers. All we can do is put large numbers in front of the formulas. So it's telling us put it in front of HCl. So on this side we can see we've got 2 Cl's but only 1 here. So we need to multiply the HCl by 2. Let's check that we've still got the right number of H's on each side. So on this side we've got 4 H's, and this side we've got 2 H's here and we've got 2 H's here, so that's 4 on that side. State what you would see during the reaction. Well, we need to pay close attention here to the state symbols. We've got a solid reacting with a solution, and that makes another solution and a liquid. So we would see that solid disappearing. It's changing into a solution and a liquid. So the barium hydroxide disappears. Then it's telling us about an experiment. A student investigated how the pH of the mixture changed as barium hydroxide was added to dilute hydrochloric acid. The student used this method. Step 1. Measure out 50 centimeters cubed of dilute hydrochloric acid into a beaker using a measuring cylinder. Use a glass rod to place a drop of the acid onto a piece of universal indicator paper and record the pH. Add 1 spatula measure of barium hydroxide to the acid in the beaker and stir. Use the glass rod to place a drop of the mixture onto a new piece of universal indicator paper and record the pH again. Repeat steps 3 and 4 until there is no further change in the pH. So basically what we're doing is we're starting out with an acid, we're adding a base to it, and we're testing the pH each time we add that barium hydroxide to see if the pH has changed. Name a piece of equipment that could be used to measure the pH of a substance more accurately than universal indicator paper. So apart from universal indicator paper, we could use a pH meter. They would allow you to say a pH probe. Explain why in step 3 the mixture was stirred after adding the barium hydroxide. Well, this is to make sure the pH or the acidity is evenly distributed. So within the beaker you don't get, for example, pH 3 and 4, that's evenly mixed, and it's also to ensure the reactants react fully with each other. And then we're given a set of results for this experiment where we've got the number of spatula measures of barium hydroxide. That's changing, that's the independent variable, and then we can see that how the dependent variable changes in response, how the pH changes as we add more barium hydroxide. Then it says plot a graph of the pH of the mixture against the number of spatula measures of barium hydroxide. When we're plotting graphs, we need to be very accurate with where we put the crosses, and it needs to be within half a small square of where it should be. So I'll quickly plot these points. And the question says use the graph to find the pH of the mixture when 4.5 spatula measures of barium hydroxide are added. So we must make sure we use a ruler here, and we're going to draw up from 4.5, see where that hits the graph, and then we're going to read off to within half a small square, and that would be 6.1. The way I've drawn it, the pH would be 6.1. Sodium carbonate has the formula Na2CO3. Sodium carbonate contains Na plus ions and CO3 2 minus ions. The atomic number of sodium is 11. What is the electronic configuration of the sodium ion? Well, we've got to remember that 2 electrons can go on the first shell, 8 on the next and 8 on the next. And when atoms become ions, they either lose or gain electrons to get a full outer shell. Now let's think about the sodium atom. It's got 11 electrons, so that would be 2, 8, 1. So the sodium ion is going to lose that electron to be left with a full outer shell, so it will be 2, 8. Explain why solid sodium carbonate cannot conduct electricity, but a solution of sodium carbonate can conduct electricity. So we've got to remember, when it's a solid, the ions are all held in place by strong forces. They're in a giant ionic lattice of thousands of ions in this kind of arrangement. So when solid, the ions are not free to move, and the reason they're not free to move is because they are held in place by strong electrostatic forces. And remember, electrostatic forces are forces between positives and negatives, in this case between the positive sodium ions and the negative carbonate ions. So that's why the solid can't conduct electricity, but when it's turned into a liquid, either by melting it or in this case by making it into a solution, those ions are then free to move about. So when in solution, the ions are free to move. So what gets us the marks in this is for saying that the ions are not free to move in a solid. Why are they not free to move? Because they're held in place by those strong electrostatic forces. But when it's a solution, then the ions can move around. Calculate the percentage by mass of sodium in sodium carbonate. So we want to know what proportion of that formula is the 2 sodium atoms. And to work out the percentage by mass, we do the total relative atomic mass of the element, so that's of the 2 sodiums, divided by the relative formula mass of the whole compound and times it by 100. So first of all, we'll work out the total relative atomic mass, AR, of sodium. In this case, we've got 2 sodium atoms, so it's going to be 23 plus 23, because it tells us each sodium atom has a relative atomic mass of 23. So altogether that comes to 46. And the formula mass, the MR of sodium carbonate, well, we've got 2 sodium atoms, so that's 23 plus 23, added onto a carbon atom, which is 12, plus oxygen, but we've got 3 of them, and each one is 16, so 3 times 16, and that comes to 106. So then the final step is to do the calculation, which it suggests here, which is going to be 46 divided by 106 times 100, and that comes to 43.39622. So we'll round that up. The 3 becomes a 4 because the next number is 5 or more. So we're going to round that up to 43.4, and that's a percentage. This question is about the extraction of metals. Give 2 advantages of obtaining metals by recycling rather than by extracting them from their ores. So first of all, it uses less energy. And if it uses less energy, that means less fossil fuels will be burned. That also means less carbon dioxide is going into the air, so there'll be less greenhouse effects caused by this process. You can also say that the mining of new ore from the ground causes environmental problems such as loss of habitats. So if you're recycling, that means that you're mining less and therefore causing less environmental problems. Small amounts of some metals are extracted using displacement reactions. In one process, zinc dust is used to precipitate cadmium metal from a solution containing cadmium ions. And we've got an equation here. Explain why this displacement reaction can be described as a redox reaction. Well, we need to remember oil rig. And oil rig stands for oxidation is loss of electrons and reduction is gain of electrons. And then we need to sort out what's going on in this equation. So the cadmium ions are gaining electrons. So that means if they're gaining electrons, that's reduction happening. Whereas the zinc atoms are losing electrons. And losing electrons is oxidation. So let's now make sure we write that in our answer. So we can say the cadmium ions gain electrons, so are reduced. The zinc atoms lose electrons, so are oxidized. So it's called a redox reaction because you've got reduction and oxidation happening at the same time. That's where that word comes from. So redox reaction because both reduction and oxidation are happening. The formula of the cadmium ion is Cd2+. The formula of the phosphate ion is PO4 3-. Which is the formula of cadmium phosphate? So we're going to use the crossover method. So we write the two ions down that it's made from. So the 2 comes down here and the 3 comes down here. So that becomes Cd3 PO4 and the 2 comes down there. One of the alternative biological methods of extracting metals from low-grade ores is bioleaching using bacteria. Give one disadvantage of this method of extracting metals from low-grade ores. The main disadvantage is it's a slow process. Lead is low in the reactivity series. Describe how to obtain a sample of lead from some lead oxide in the laboratory. Well, what we would do is we would heat it with carbon, and what happens is we've got lead oxide plus carbon. Carbon is more reactive than lead, so it can displace the lead and pinch the oxygen, so that forms carbon dioxide and lead. And your 2 marks for this question are for saying use carbon and use heat. Question 4. Water acidified with dilute sulfuric acid was electrolyzed for 10 minutes using inert electrodes. And here we can see the electrolysis cell. In this electrolysis, the acidified water is an electrolyte. Explain why acidified water is an electrolyte. Well, it's because it contains ions and those ions can move. Hydrogen collects at the negative electrode and oxygen collects at the positive electrode. Which of these shows the results after 10 minutes of this electrolysis? So first of all, I'm going to label which way round it is. So oxygen collects at the positive electrode and hydrogen collects at the negative electrode. Now the only difference between these diagrams is the relative proportions of these two gases, and we've got to remember they're being made from H2O. So when that is split apart by electrolysis, there's going to be twice as much hydrogen compared to oxygen. So when we look at these diagrams, diagram A is correct because we can see there's twice the volume of hydrogen compared to the volume of oxygen that's been collected. Complete and balance the half equation for the formation of oxygen at the positive electrode in this electrolysis. So it's asking, how do we get oxygen gas from these hydroxide ions? Well, I'm afraid this equation is one that you're probably just going to have to remember. They break down to form 2 water molecules and an oxygen molecule, and also 4 electrons. And if I try and explain how that happens, well, if we think about these 4 hydroxide ions, there's 1 water molecule, here's another water molecule it splits into, so they're the 2 H2Os. Here's the oxygen molecule, and then we've got 4 electrons left over. Copper sulfate solution was electrolyzed for 10 minutes using copper electrodes. Figure 3 shows the mass of the cathode and the appearance of the copper sulfate solution before electrolysis and after electrolysis. So we can see the mass of the cathode increases, but the copper sulfate solution has no change. It says describe what should be done to the copper cathode after it has been removed from the copper sulfate solution before its final mass is determined. Well, it might have some of that solution on it. So the first thing you need to do is rinse it, and then we need to dry it with a paper towel. Explain in terms of ions the change in mass of the cathode shown in figure 3. Well, we need to remember the cathode is negative. How do we remember that? We remember the word panic, which stands for positive anode, negative is cathode. So we've got the negative cathode here, and we've got some copper ions which are positive moving towards it. So what happens is the copper ions are attracted towards that because opposite charges attract, and there they will gain electrons and form copper. In other words, they changed into copper atoms. So in our answer, we're going to say the copper ions, Cu2+, are attracted to the negative cathode, where they gain electrons to form copper atoms. Explain why the appearance of copper sulfate solution did not change during electrolysis. So we've got the negative cathode over here, and we've got the positive anode over here. And both of them are made out of copper. So what's happening is we've got copper ions in the solution, which is causing that pale blue colour. And we've already said the copper ions move across here where they turn into copper atoms. So they're leaving the solution. But at the anode, some of that copper is turning into copper ions, and they're entering the solution. So the number of copper ions in the solution is staying the same. And the way we can explain that is copper ions enter the solution at the anode and leave the solution at the cathode. So the concentration of those copper ions stays the same. If that was building up, it would get more dark in colour. If we were losing copper ions overall, it would get paler in colour. But because we're replacing those copper ions at the anode, as they're being taken out of the solution at the cathode, then the concentration of copper ions stays the same. This question is about the properties of different substances. Silicon tetrachloride is a simple molecular covalent compound. A molecule of silicon tetrachloride is composed of a silicon atom and 4 chlorine atoms. A silicon atom has 4 outer electrons and a chlorine atom has 7 outer electrons. Draw a dot and cross diagram of a molecule of silicon tetrachloride. So let's first of all start off with that silicon atom, and we're only showing the outer electrons. It's in group 4, so it's got 4 outer electrons. Chlorine has 7 outer electrons, so each chlorine atom needs 1 more to be stable, so it shares with silicon. So the chlorine has 1, 2, 3, 4, 5, 6, 7 crosses, plus it's sharing the dot from silicon, that gives it a full outer shell. Same for this chlorine atom. Same over here. So each chlorine atom still has 7 crosses of its own. It's in group 7, so it's got 7 electrons in the outer shell, but with the one that it's sharing with silicon, it's got a full outer shell because it's now got 2, 4, 6, 8. And the same over here. Explain why simple molecular covalent compounds such as silicon tetrachloride have low melting and boiling points. So I'm going to draw a quick diagram to remind you about the bonding in simple molecules. So here I've got 3 molecules of silicon tetrachloride, and they are held together with these strong covalent bonds holding the silicon and the chlorine atoms together in each molecule. However, between the molecules we've only got weak forces of attraction, which I'm going to show with these dotted lines. And it's these weak forces that give rise to the low melting and boiling points. So we can say they have weak. Now, because they're between the molecules, we call them intermolecular. Inter means between. Weak intermolecular forces. So when you start to heat it up, it doesn't take much energy to break these forces, so these molecules can start moving apart and behaving more like a liquid or gas. So the weak intermolecular forces don't need much energy to break, or you could say overcome, the forces. Part of the structure of rubidium bromide is shown in figure 4. So we've got rubidium ions Rb+, and we've got bromide ions Br-. Which row shows the most likely melting point and boiling point of rubidium bromide? Well, we need to remember that this giant ionic lattice is held together by very strong electrostatic forces that do need a lot of energy to break. So it's going to have high melting points and high boiling points. So let's pick the highest melting point and boiling point. Answer D. Diamond and graphite are 2 forms of carbon. Figure 5 shows how the carbon atoms are arranged in a part of the structure of each of these forms of carbon. So this one is showing diamond and this one is showing the structure of graphite. Diamond is one of the hardest known substances on Earth and is used in cutting tools. Graphite is soft and flaky. Diamond is a poor electrical conductor, but graphite is a good electrical conductor. Explain in terms of structure and bonding these properties of diamond and graphite. So we've got diamond being hard. Now, first of all, diamond is hard because if we look at each carbon atom, it's making 1, 2, 3, 4 very strong covalent bonds. So 4 other atoms are holding onto it very strongly. So we're going to say diamond is hard because each carbon atom is held in place by 4 strong covalent bonds. Then we need to say why graphite is soft and flaky. Well, we need to remember the carbon atoms are arranged in layers in graphite, and between the layers we've only got weak forces of attraction. So that means the layers can slide past each other, and that's what makes it soft and flaky. So we're going to say graphite is soft and flaky because the atoms are arranged in layers and the forces between the layers are weak, which means the layers can slide past each other. Now we need to explain why diamond is a poor electrical conductor but graphite is a good electrical conductor, and we need to remember what the bonding is like. So in diamond, here's carbon with its 4 outer shell electrons. It's bonding with 4 other atoms. So it means each of those electrons is involved in bonding. So there's no free or delocalized electrons. Whereas in graphite, the carbon atom is here with its 4 outer shell electrons. This time it only bonds with 3 of these electrons. It makes 3 covalent bonds, and that leaves an electron spare. This is a delocalized electron that is free to move through the structure. Okay, so let's start forming our answer. Diamond is a poor electrical conductor because it does not contain delocalized electrons. Graphite does have delocalized electrons, and we need to say these electrons can move through the whole structure, which can move through the whole structure and carry the current, or you could say carry the charge. An investigation was carried out on the reactivity of 4 metals D, E, F and G. Equal sized pieces of these metals were placed in excess dilute hydrochloric acid and left for 3 minutes. Figure 6 shows the observations of the reactions for metals D, E and F, but there's nothing for G. The order of reactivity of these metals is shown. So the most reactive was E, then D, then G, then F. Use the information in figure 6 and figure 7 to suggest the observations that would be made for metal G. So we need to realise that it's not quite as reactive as D, but it's more reactive than F. So in terms of bubbling, D bubbles quickly and F, there's just a few bubbles. So let's say that it will be somewhere in between that. So we would say it bubbles steadily or slowly, you could say. And we can also see that after 3 minutes there's none of metal D left, it's all been used up, whereas metal F looks unchanged. So we'll go somewhere between the two and say that there was some of the metal was left. So some of it had been used up, but some of it was left at the end. The dilute hydrochloric acid used in this reaction is a strong acid. Explain the meaning of the terms dilute and strong. Well, dilute is how much water has been added to a chemical. So if it's been watered down a lot, we say it's dilute. If it's more of the chemical and less water, we say it's more concentrated. So dilute means there is a low concentration of hydrogen ions. Remember, it's hydrogen ions that make an acid an acid. That's what gives it its acidity. So in other words, compared to the amount of water around, there's not much hydrogen ions in a large amount of water, a low concentration. The strong acid, that's to do with the acid itself. And if it's a strong acid, then it fully dissociates to produce hydrogen ions. So to give you an example, if we had hydrochloric acid, that entirely breaks down to give lots of hydrogen ions and also chloride ions. The whole thing breaks down. It's a one-way reaction. Whereas a weak acid, you would see a reversible reaction sign there, because weak acids partially break down, but they also reform, so they wouldn't produce as much hydrogen ions. Here's a challenging question, no surprise there, because we're getting towards the back end of the paper, and as you go through the paper, the questions do get more challenging. The formula of lead ethanoate is PbCH3COO, and that's in brackets times by 2. Calculate the number of atoms that combine together to form 16.25 grams of lead ethanoate. So I'm going to need to work out the moles. And remember, moles equals mass over mR. Now the mR of this lead ethanoate is going to be 207 for the lead, And then we need to remember that everything in here is multiplied by 2. So we've got 2 carbon atoms there, but we've multiplied it by 2, so we've got 4 carbon atoms. So we'll do the 4 times 12 for each carbon. And we've got 3 hydrogen atoms, but multiplied by 2. So I'm going to do 6 times 1, which is the relative atomic mass of hydrogen. And oxygens, we've got 2 there, but we've multiplied it by 2, so we've got 4 oxygens, so I'll do 4 times 16. And when I add all of that together, the MR of the lead ethanoate is 325. So, remember, moles is mass over MR. We've got 16.25 grams. So that's going to be 16.25 divided by the MR, which is 325, and that gives me 0.05 moles. Now, if we want to know how many molecules of this there is, we need to multiply the moles by the Avogadro number. So, molecules of lead ethanoate is 0.05 times 6.02 times 10 to 23, because that's the number of particles in a mole. So if we multiply it by this, it gives us 3.01 times 10 to 22. So that's the number of molecules of lead ethanoate. But it's asking me for the total number of atoms. So we need to know how many atoms in each molecule. We've got 1 ppb, we've got 2 carbons multiplied by 2 is 4 carbons. We've got 3 times 2, 6 hydrogens, and we've got 4 oxygen atoms altogether. So altogether we've got 15 atoms in that molecule. So the total number of atoms altogether is going to be 15 times 3.01 times 10 to 22, which comes to 4.515 times 10 to 23. Iron is more reactive than copper. Iron will displace copper from copper nitrate solution. 2 possible balanced equations for the reaction are this. So the difference is the balancing numbers in front, the ratios. It was found that 2.24 grams of iron reacted with excess copper nitrate solution to form 3.81 grams of copper. Carry out a calculation using the information above to show which equation represents the reaction taking place. So we're going to say moles of iron is mass over AR, which is going to be 2.24 grams of iron divided by the AR of iron, which is 56. And that comes to 0.04 moles. For the copper, moles of copper equals mass over AR, which this time is going to be 3.81 divided by 63.5. So that gives us 0.06 moles. So that is of the copper and this is of the iron. So 0.04, 0.06, that's a ratio of 4 to 6, and we could simplify that by dividing into, that's a ratio of 2 to 3. While equation 1 is a ratio of 1 iron to 1 copper, equation 2 is a ratio of 2 iron to 3 copper, which is what we've got here, 2 to 3 ratio. So the correct one is equation 2 is correct. If you found this video useful, please give it a like and don't forget to subscribe.